my name is Sophie Terian. I'm a junior studying chemical engineering at the University of Kansas. This summer, I interned with Ducommun Aerostructures. It was an absolute joy to work there and to work with PPI. I'm very honored to be here today, even on Zoom, talking to you all. So we're going to start off reviewing the waste management hierarchy. Then we'll talk a little bit about Ducommun. We'll talk about the projects that I was working on. We'll end by talking about the KDHE Environmental Stewardship Award, and then discuss some future projects for the company. So a lot of you in here probably already know about the waste management hierarchy, but I wanted to review in case you don't. It's basically a strategy for how we deal with waste. So the whole idea is if you can prevent the production of a harmful substance in the first place, then you don't have to spend any effort trying to deal with it after it's produced. So while things like recycling and treating are beneficial and definitely better than disposing or releasing of the substance directly into the environment, those processes can be fairly energy intensive and so require labor be put into that. So thus, the P2 mantra that our interns use is change the material, change the technology, or change the process in order to achieve the source reduction of pollutants. So an overview of Ducommun. Ducommun Incorporated is a California-based company. It was founded in 1849, actually a few months before California was even a state, which is really cool. Nowadays, the products they make are for commercial aircraft platforms, mission-critical military and space programs, and industrial applications. And in 2020, the company was valued at $628.9 million. So the Parsons location is one of several across the country. Their specialty is in titanium, and specifically titanium hot and superplastic forming. So they also do 5-axis machining and laser cutting, different kinds of chemical processing, milling, different kinds of painting, and non-conventional machining. So the first week I was there, my mind was blown when I found out that 4,000 different parts can be produced in this facility. So it's definitely not just mass manufacturing environment, it's custom fabrication, and the products are very cool. So this diagram above is meant to give you a good mental image of some things that can come out of here. So we start with sheet metal. By the time it leaves, you can get curvy parts, parts with very precisely drilled holes, very three-dimensional things, gradients of thickness, different kinds of paint. So as you can imagine, for a P2 project where we're trying to figure out emissions associated with different processes and how much emissions will occur in the future, it can be difficult when you've got 4,000 different parts. So instead of normalizing our measurements via part, throughout the presentation, you might hear me talk about labor hours. So we essentially looked at what was being produced, like emissions per labor hour in a section of the facility. So the first project I'm going to talk about is the one I spent the most time on, which is the chemical milling and etching process. So this is a very simplified process flow diagram of what goes on at the facility. On the left there, you can see we start with a little piece of titanium. First, it gets sprayed with a maskant, which is an acid-resistant material. It protects the metal from being corroded where it is applied to the metal. So it's sprayed on as a liquid and then it solidifies. And once it solidifies, you can scribe out pieces of it selectively to expose selected pieces of the metal. Then that scribed piece is set into the first tank, which is an acidic tank. And for titanium, you actually have to use hydrofluoric and nitric acid, which definitely presents some safety concerns, but titanium is very corrosion resistant. So these acids are necessary. Then the piece is rinsed off. And at the very end, the maskant is pulled off, the remaining maskant, and you wind up with a little piece of metal that has been corroded in selected places. It's often used to achieve tight weight tolerances, and it's a very precise system. So if you know the concentration of acid in the tank and you know the temperature of the tank, you can figure out the rate that the reaction is occurring at. And based on that, you can plan how long you leave the piece in the tank, and you can very precisely figure out how much material will be taken off of this metal. So the reason we looked at this process is because historically it's accounted for more than 85% of total hazardous waste at the facility and 65% of toxic releases. The good news is that Ducommun has been trying very hard to reduce this hazardous waste over the past few years. So once I normalized the data to the pounds of emissions per hour, so pounds of hazardous waste per hour, this is accounting for varied production levels. It's controlling for that. So once you do that, you can see that there's been a 70% reduction in hazardous waste since 2019, which is really good. However, there are still large volumes of hazardous waste being produced, and this waste is hazardous due to its pH, which is about 2, and its chromium and lead content. There's another problem, which is that large amounts of acid are required to make this reaction proceed. And then there's a quality issue with staining on parts, which correlates with the production of hazardous waste. So when this staining occurs, that is when operators know they need to extract spent acid and add virgin acid to the solution. So if you could reduce the frequency of the staining and you could keep the etch rate or the rate that the reaction is happening in the correct parameter, then you can reduce how often hazardous waste extractions need to occur. So if you like chemistry, there at the bottom, I went ahead and put the literature accepted reaction. It's really interesting to note that the reaction will not proceed without both hydrofluoric and nitric acid. So my research and calculations were multifold. One was to deal with where the chromium was entering the solution. Sadly, I did not have time to get to lead in my time here. But this diagram at the top shows you the potential places that chromium is entering the process. So the labels in red show the materials which contain chromium, and the labels in blue, those materials do not contain chromium. So our main culprits here are the stainless steel baskets and fingers, the stainless steel lids, and then there's also some Hastelloy X materials that enter. So the biggest culprit was actually the lids. So this is the acid tank, and you can see the lids have this greenish buildup, and we know that chromium oxides are green. So this is the first place that the company should investigate to see if this is a source of chromium in the solution. The next thing I looked into were potential treatment exemptions under RCRA for hazardous waste. So this was saying if it would be possible to remove chromium and lead from the solution via source reduction, then the only problem with the waste is that it has a low pH, and then under RCRA treatment exemptions, what can we do with it? Then the next thing I looked into was extending the tank lifespan. So this is your very strictly P2 solution of reducing hazardous waste at the source. If you can reduce the extractions, you reduce hazardous waste. So basically we needed to know what's causing the staining on these parts, and that's a picture of it right there. So the solutions we came up with were, for the source reduction of chromium, was to use this thing called plastisol. So I was able to talk to one of the other locations of Ducommun in California, and they coat their stainless steel baskets in plastisol, and it prevents them from being corroded and contributing chromium to the solution or whatever else it might contribute to the solution. So this is a good starting point. Also replacing the lids with something like a polypropylene lid, and replacing the fingers with something like rubber. As for the acid reduction, we would be looking into an acid filtration system. So I was able to talk with a chemist who worked at Ducommun for 11 years about this. The acid filtration module uses gel exclusion chromatography, and it basically purifies the acid. It removes the metal ions from the solution, and that metal builds up over time as you put metal in an acid. So it's able to filter that out. However, these systems are just inherently not super efficient, and they also have an inherent tendency to get clogged because you're running the liquid through a solid bed. So this location actually had one of these acid filtration modules back in 2018. However, it only worked for 3 months before it clogged. So this is not a super appealing option for the company. So if source reduction could be achieved for the metals, then perhaps the most cost-effective option would be to treat the hazardous waste on-site under RCRA exemption. So this would just be neutralizing the pH in an ancillary system and sending it back to the wastewater treatment plant after it's been neutralized. So because this project was so complex, I was not able to come up with any definitive solutions. However, I was able to calculate that there are potential savings of up to 5 pounds per hour of liquid hazardous waste if hazardous waste could be eliminated, and that would amount to $30,000, more than $30,000 in 2022. All right, so the next thing we're going to talk about is the maskant. The problems here are that the maskant being used is a toluene-based mixture at 65% weight toluene, which is a volatile organic compound and a hazardous air pollutant. So 65% of the toxic releases at the facility come from the maskant process, or toluene being used. There's also large amounts of overspray, and toluene is the only reason why this facility is under a Title V air permit, which costs about $1,500 annually. So what I looked into here was basically, 1, can we substitute the chemical? And 2, how can we reduce the waste and the overspray associated with this process? So the solutions were to look into a few different types of maskants, which we'll talk about in the next slide. And then as for the process changes, refer to this diagram. So the top image with they kind of look like bats, but they were triangular pieces hanging down. This is how they were being hung at the facility. And as they would spray maskant across these pieces, there was lots of maskant that would get wasted in the gaps. However, if the operators would have hung the pieces so that the gaps were minimized, flipping one of the triangular pieces up and down, you would reduce overspray associated with the process. So this was just operator training and reducing gaps between parts. I also looked into the transfer efficiency of the gun that was being used. So these three pictures here show the different maskants I looked into. The most cost-effective one was parachlorobenzoyl trifluoride. However, it is not allowed to be used on titanium because it contains halogens, and that presents a quality control issue. So then I looked into HydroMask, which is a water-based maskant, and the process is very similar to the one currently being used. Then there's PhotoCure, which is completely different. It's really cool. It is able to instantaneously cure under UV light. So even though PhotoCure represented a very large price increase, the company was still interested in this as a solution because of its potential to decrease labor costs and quality issues associated with the maskant. They were also very interested in the environmental benefit from this and getting out of that Title V air permit. So the savings here, but if they switched, would be up to 14,000 pounds of VOCs and HAP reduction. And then if they could reduce overspray associated with the process, the savings are kind of small due to the type of gun being used. So it's an airless sprayer, and airless sprayers have a maximum transfer efficiency of about 60%. Based on my experimental data, there's currently a 44% transfer efficiency, which with that type of gun just doesn't leave much room for improvement. However, because there's no capital expenditure here, it's a worthwhile solution to try to start implementing. So then with energy reduction, I was able to examine compressed air leaks and if machines are running when they need to be running. So the solutions were to walk around the facility with an ultrasonic leak detector and detect the air leaks, note their location, and then to study what machines were running when and if they needed to be on at that time. So the compressed air leak repair had less than a 1-year return on investment and would save about $3,000 and 35 metric tons of carbon dioxide equivalent emissions. The lighting upgrades had a longer return on investment. It was about 4 years. The facility has a ton of fluorescent, so this was calculated based on updating the fluorescence to LEDs. And this would save a lot in the end after the 4-year period. It would save $63,000 annually and 669 metric tons of carbon dioxide equivalent emissions. The run times were actually not profitable in the end. And this is because this would deal with turning machines off overnight or on the weekends when they don't need to be running. However, the warm-up times associated with some of these machines could be like 30 minutes to an hour to warm back up. So therefore, the labor costs associated with turning them off, turning them back on, and then waiting for them to warm up, that was actually more expensive than the savings. So there was no profit here. Next, I looked into plastic water bottle reduction. So Ducommun is really great about providing their employees with water, which is really good in the hot parts of the facility. However, there's no recycling in Parsons, so all of this was just turning into single-use plastic. So I looked into replacing plastic water bottles with reusable metal water bottles and installing some refill stations around the facility. Also installing filters on the water fountains because everyone was very concerned about water quality, which is good. And even with all these installations, there was less than 1-year return on investment, $11,600 in savings annually, and about 1 metric ton of carbon dioxide prevented. So then similarly, I looked into plastic reduction in packaging. So the problems here were that it is important to wrap the parts in plastic before they leave the facility in order to prevent quality issues like scratches. However, over time, the excess plastic on these parts was adding up. So I actually went around the facility and measured the excess length on like 850 parts. And I was able to find that on average, there's about 6 inches of excess polytubing per polytube part. And you can see that roller there, that's the polytube bag. So they have the part, they kind of estimate how long the bag needs to be, and then they cut it, and they'll cut as many bags as they need to for the parts. And if the part is curvy, this presented a problem because it's hard to visually estimate how long your bag needs to be for a curvy part. And it's also hard to measure that with the tape measure. So that's where this excess plastic was coming from. So the solutions were actually really easy for this one. It was just a soft tape measure, so you can measure those curvy parts a lot more easily and get more accurate length, and then also creating linked lists for standard pieces. So even though there's up to 4,000 different parts that can be produced, there's a lot of parts that come through very frequently. And for those ones, if you had some, links of standard pieces, that would help. So again, this is an immediate return on investment. It's just a simple process change and a tape measure. So it could save $4,751 per year, and again, about 1 metric ton of carbon dioxide equivalent emissions. So this is the last project that I was looking at, and it's not fully fleshed out yet, but it's a water reduction idea. So this is a partial process flow for the chemical etching and milling process. After the part comes out of the acid tank, it needs to be sent through a series of rinse tanks. So that's that metal piece moving to the right. However, the water is moving backwards through the tanks. It's moving to the left. So it's going from the cleanest tank to the dirtiest tank, which is a really good water conservation method already. But basically after the water is used, it's treated back up to a safe pH and sent to the wastewater treatment plant and not used by the facility again. So the proposition here would be to make a closed loop system. So there's already a reverse osmosis system at the facility to clean the water from the city before it goes into the tanks. So the idea would be after treatment to send it back to the RO system, clean it and send it back through the tanks. So even if the water can only be cycled through 2 or 3 times, that would still be an improvement and a significant water saving from what is currently going on. And the company was very interested in this idea. So the research here would just need to be how effectively can the RO system clean, and is it compatible with how dirty the dirtiest tank is? But the potential savings would be up to 300 gallons per hour and about $2.40 per hour. So then future projects that the company could also look into includes hazardous waste from painting reduction. So currently the hexavalent chromium painting is operating in the same area as the non-hexavalent chromium painting. So all of that material is hazardous waste by the time it leaves. So if you were able to separate those two, then only the hexavalent part is considered hazardous. The next thing would be to analyze MEK versus MPK as a solvent for cleaning. Now that MEK has been taken off the hazardous air pollutant list by the EPA in 2005. So this would involve test cleaning dirty parts with each solvent and recording the volume of solvent used to see which one is actually more fit for the process. So MEK is more concentrated, so it's possible that you would actually use a lower volume of MEK than they are currently using for MPK. The last potential next idea would be switching from the paperwork orders that the facility uses to kiosk work orders, going digital. Other Ducommun locations have been going paperless, so this should be a change that's coming in the next few years and would significantly reduce paper usage. So the last thing I wanted to talk about was the Environmental Stewardship Award that the Kansas Department of Health and Environment offers. Sadly, this year it was canceled due to the pandemic, but we're hoping it'll be back up next year. Ducommun is eligible because of their efforts to reduce hazardous waste. So like I mentioned earlier, there's been a 70% reduction of liquid hazardous waste since 2019, and it's been a steady decrease as they've been able to implement some process changes here. Basically, all they've been doing is making sure that these extractions only occur when it's absolutely necessary instead of preventatively or instead of on a routine schedule. So make sure you're only dumping when you absolutely have to do this extraction. And then the other thing they've done that qualifies them is switching off of perchloroethylene-based maskant onto a toluene-based maskant over 2018 to 2019. So in the end, all the projects combined saved about $100,905, 706 metric tons of carbon dioxide equivalent emissions, 2,100 pounds of solid waste, 33,158 kilowatt hours, and 16,904 pounds of VOCs/HAPs. So does anyone have any questions?